Right, in the second part of this course, which is a much shorter section, we're going to very briefly look at mass spectrometry and how you can get structural information from mass spectrometry. I'd just like to remind you what mass spectrometry is, and this is from the first year text. Is what happens is you have a sample, and in this example we see here the sample is neon, and the neon is allowed in a small amount into a vacuum chamber, and as the neon passes through this area is between a heated filament and a positive plate, and the heated filament is highly negative. The heated filament it's so hot that there are electrons around it. Those electrons are pulled off by the positive plate, and these electrons come at high speed past the neon atoms that are coming in, and these electrons actually knock off another electron from the neon, so the neon ends up with a positive charge even though there are electrons going past. So the neon ends up with a positive charge. It's then accelerated by this negative grid, and then there's some slits there that are collimated, and of course because it has a charge, any charges moving in a magnetic field follow a curved path, but of course depending on its mass will depend on the change in momentum of the particle, and so you'll be able to, on the detector, you'll be able to pick up the different masses. And of course neon has different isotopes, so you'll have a mix of different masses of neon coming in, and then you will find on the detector you can see the signals due to the different masses of particle coming through. Okay. Important thing is that you can only see particles that have a charge. If it does not have a charge, it will not be deflected by this magnetic field, and so you will not see any signal from a particle that does not have charge. This is called electron impact mass spectrometry. There are other types of mass spectrometry which we'll not deal with, but this is electron impact mass spectrometry. Point to note is that if you've got a molecule coming through, that your molecule will also have energy as it comes through, and that energy has interesting consequences, as we will see. So here is what happens when you put methanol through a mass spectrometer using electron impact mass spectrometry. What is interesting about it is that yes, you see ethanol coming through with a charge because it's had an electron knocked off it, so you see methanol plus coming through, and that's this peak at 32. That we call the molecular ion. But what is interesting about methanol is that methanol has been provided with enough energy during this impact process that it starts to fragment, it starts to break apart. And so in the mass spectrometer, you're not only seeing methanol of mass 32, but you're seeing a mass 31, mass 29, and a mass 15 coming through. So that is quite interesting. Whenever you come to a mass spectrum, I want you to look for two things. I want you to look for the molecular ion, and the molecular ion is quite easy to find because we know that methanol is CH3OH, which means it's got 4 hydrogens, 1 carbon, 1 oxygen. So we can quickly calculate, because carbon has mass 12, hydrogen has mass 1, oxygen has mass 16, we can calculate what 4 hydrogens is. 1 carbon is 12, that's a total of 16. 1 oxygen is 16, and that together makes 32. We can calculate the mass, and we see that it correlates with the molecular ion that we have here. Okay, so the molecular ion is the mass of the ion, and we can check it against the compound that we're working with. However, there's another peak that's also important, and that's the base peak, and it's always scaled to be 100. It's the most intense peak in the mass spectrum, and what that tells us it tells us what the most stable fragment is that is formed in the mass spectrum. So really, there are two peaks that I want you to look carefully for. One is a molecular ion, which is it will be the mass of the molecule that has not fragmented at all, and the base peak is the fragment that is most prevalent, that's most stable, that is observed in the mass spectrum. Okay, so it's really interesting, and I want you to have a look carefully that there are other peaks that we haven't dealt with, like there's this peak at 33. We need to figure out how on earth, with methanol, with one oxygen of mass 16, one carbon of mass 12, and 4 hydrogens of mass 4, how on earth could we possibly get a mass of 33? Well, the answer is that one of the carbons does not have mass 12. So a small fraction of the sample does not have mass 12. Remember from NMR that carbon 13 is 1% of all carbon. So in your mass spectrum, 1% of all your methanol is going to have carbon 13 in. And when you calculate the mass of 13 plus 16 plus 4, you get a mass of 33, not 32. So do expect that you will have a very, very small amount of mass 33 in the spectrum for methanol. So don't forget that the mass, that the isotopes are still, the natural abundance isotopes are still prevalent in all your molecules, and so we will end up getting that visible in the spectrum. Okay. So what I want to just have a look at is just how do we represent all of this. So have a look here. This is what happens in the mass spectrometer is you have a methanol molecule. It gets hit by a high energy electron, and that electron kicks off another electron, so you get 2 electrons at the end. But of course it kicks off in your methanol you've only got pairs of electron. It kicks off a single electron, which means that you end up with an unpaired electron, and so what you end up with is called a radical cation. And this radical cation we can work out is mass 12 plus mass 4 from the hydrogens plus mass 16, so that's mass 32, and because it has a charge it is picked up in the mass spectrometer. It is an energized odd electron ion. It is called a radical cation. Now we know in methanol that we have got lone pairs on the oxygen. The lone pairs are the most likely electron speed lost. Some molecules don't have lone pairs, so in the mass spectrometer, if there are no lone pairs, it's quite likely that pi electrons will be lost. If you've got no lone pairs or no pi electrons, then of course the only electrons you can lose are sigma electrons. But again, remember that from your pair of electrons, you'll have all pairs normally in a molecule. When you kick off an electron, you'll end up with an unpaired electron, and so your resultant will be a radical cation. Note that if there are any uncharged fragments, they will not be observed, and you will only see positive ions in the spectrum. So to just illustrate what I mean by that is have a look at the mass spectrum of hexane. Now in the mass spectrum of hexane, note that of course there are no lone pairs for hexane and there are no pi electrons for hexane, so of course the electron that will be lost is a sigma bonding electron, so from a pair you will lose one of those electrons. Now of course when your radical cation for hexane fragments, it'll fragment into a cation and a radical, and there are several ways in which it can fragment. So for example, it could fragment forming the methyl cation and C5H11 radical, or it could fragment this way, or could fragment that and that and that. And you'll notice that I've only put numbers. So this 15 that I've got here is 12 for the mass of carbon and 3 for the mass of a hydrogen is 15. This 29 I've got here is 2 times 12 for 2 carbons plus 5 for the 2 hydrogens. I've only put the mass next to the positively charged one, because remember that uncharged fragments such as radicals will not be observed in the mass spectrum. Your radical cation will be observed, but a radical without a charge cannot be bent by the magnetic field. It cannot follow a curved path in the magnetic field, and so you will not see a peak on the mass spectrum from these. So what's interesting here is, let's see what we've got. So I'm not showing, I haven't got the spectrum spread out enough to see the molecular ion. So the molecular ion is somewhere to the right. We can't see it in this. We can calculate what it is, 6 times 12 plus 14. It's not there, but we can see what the base peak, and the base peak is at 57. The most stable one is at 57. But be careful what we mean by most stable. Surely a large cation is more stable than a slightly smaller cation, because you've got more of a system to stabilize that positive charge. But here's the interesting thing about mass spectrometry, is mass spectrometry isn't just about the things you see, it's also about the things you don't see. So yes, while this fragment of mass 71 might be the most stable, to form it you have to form a very small radical, which is a really unstable radical. So the peak you see at 71 is small, because to form that you have to form something that's really, really unstable, even though you don't see it. And it seems that at 15 you might just be able to see a very small peak at 15. Of course, you've got a really unstable carbocation there, so it's going to be very, very small. And you can see that as the carbocation gets larger, yes, you start to see more of it appearing, but of course the most stable pair, so this particular pair of a cation and a radical is most favored, because the pair overall has a greater stability than any of the other pairs. So that is the important thing to note. So what we have is that even though the radical is not seen, its stability influences the fragmentation. The favored fragmentation is determined by the stabilities of both the cation and the neutral fragment, neutral radical produced by fragmentation, even though you don't see it. Larger is more stable, and recall your carbocation stability: tertiary, secondary, primary, methyl, and of course these are mainly primary, except for that, and of course the larger the primary, the slightly more stable it is. Okay. Just while we're speaking of isotopes, please don't forget that your halogens, bromine occurs in nature in a 1-to-1 ratio, an almost 1-to-1 ratio of bromine 79 to bromine 81. You can see that the mass there is 2 apart. So when you see pairs in the mass spectrum, it's quite likely that you have bromine. Can you see that with bromoethane, when you fragment it, can you see that you can see there's the Br81 plus and the Br79 plus. They're 2 units apart. The pair are seen there. That is fragmented right down to the bromine. But of course, what you also see is these pairs of your molecular ion as well. Okay, so please look for pairs where you've got pairs 2 apart of equal intensity, pairs of peaks. It's quite likely that you've got bromine, because bromine occurs into 1-to-1 ratio as seen. Right. With chlorine, Don't forget that chlorine 35 to 37 occurs into a 3 to 1 ratio. So again, when you see a 3 to, so benzyl chloride has a chlorine in it, and you see a 1 to 3 ratio. That 1 to 3 ratio is indicative that there is a chlorine atom present in your molecule. Of course, don't forget that you have a base peak. In this case, the molecular ion is 126, it's of chlorine 35, but you see an M plus 2, from that a third intensity, chlorine 37, that is present in the molecule. Okay, over here I've got a table of isotopes, so just have a look and see. So these are relative abundances, so your major isotope is given with a relative abundance of 100, and so you see with carbon you've got an M plus 1 isotope, that is about 1%. For nitrogen you've got an M plus 1, that is about 0.5%, and sulfur you've got an M plus 1, that is about almost 1% as well, plus an M plus 2 about 4%. So please look for those. There's also the oxygen 18, which is 0.2%. Of course, bromine, we've got almost a 1-to-1 ratio of bromine 79 to bromine 81, and chlorine we've got a 1 to 3 ratio, or 3-to-1 ratio of 30 chlorine 35 to chlorine 37.